Contemporary space exploration and aerospace engineering are standing at a historic inflection point. For decades, the industry relied entirely on disposable launch vehicles, highly reliable, incredibly expensive rockets that ended up at the bottom of the ocean after a single use. But today, that methodology is being actively rewritten by the Starship program. Conceived by SpaceX, what began over a decade ago as an abstract concept for the colonization of Mars has evolved into the largest, most powerful launch vehicle humanity has ever constructed. It dwarfs the Saturn V of the Apollo era, and it eclipses NASA's Space Launch System in thrust, payload volume, and sheer operational ambition. But how did SpaceX actually build it? Historically, government agencies rely on decades of exhaustive computer simulations and massive budgets before they ever build a single piece of flight hardware. SpaceX threw that playbook out the window. They adopted an industry axiom: test like you fly. They embraced an aggressive, iterative development philosophy. They accepted a calculated tolerance for risk, allowing hardware to fail during testing to learn faster. Over the past decade, this architecture transitioned from a theoretical carbon fiber concept into a constantly mutating stainless steel colossus, culminating in the current Block 3 generation and the dramatic events surrounding Flight 13 in July 2026. This is the complete evolutionary history of Starship, step by step, test by test. The carbon fiber dead end. The initial push for a super heavy vehicle started way back in 2005. But the modern architecture really began to take shape around 2012 under the name Mars Colonial Transporter, or MCT. The goal was almost biblical in scale: transport up to 100 passengers at once, along with enough cargo to build a self-sustaining infrastructure on Mars. By September 2016, the project was formally renamed the Interplanetary Transport System, or ITS. The proposed vehicle was a Titan. It featured a core diameter of 12 meters, standing 122 meters tall. The first-stage booster was designed to use 42 Raptor engines, generating an unfathomable 128 meganewtons of thrust at liftoff. To make this work, the technical feasibility relied heavily on advanced carbon fiber composites for the cryogenic propellant tanks. Carbon fiber has an exceptional strength-to-weight ratio, which is absolutely critical to keeping the vehicle's dry mass low enough to carry heavy payloads to other planets. By late 2016, SpaceX actually built a full-scale 12-meter carbon fiber tank to test this theory. But then, the reality of physics set in. During empirical tests on a barge in Washington state, SpaceX subjected this giant tank to extreme cryogenic pressures. The result was a catastrophic failure. The tank violently ruptured, sending fragments dozens of meters into the air. The core issue was how carbon fiber interacts with pressurized liquid oxygen. When you mix organic carbon compounds and binding resins with pure liquid oxygen under extreme mechanical stress, any microcrack can cause solid oxygen to form, leading to instant explosive combustion. This was the exact same chemical phenomenon that destroyed a Falcon 9 rocket back in 2016. Furthermore, manufacturing carbon fiber at this scale was an absolute logistical nightmare. You would need massive, incredibly expensive curing ovens, known as autoclaves, just to bake the 12-meter segments. It would completely bottleneck the rapid production rate needed to build a massive fleet for Mars. SpaceX realized a hard truth: carbon fiber was a dead end. The stainless steel revolution. Between 2017 and 2018, the vehicle was scaled down to a 9-meter diameter. But more importantly, SpaceX made the most consequential engineering decision of the entire program. They completely abandoned carbon fiber and advanced aerospace aluminum, pivoting entirely to 300 series austenitic stainless steel. This sent shockwaves through the aerospace orthodoxy. The industry is obsessed with reducing dry mass using the lightest materials possible, and steel is heavy. but the decision was rooted in thermodynamics and manufacturing reality. Traditional aluminum-lithium alloys are incredibly difficult to weld at a 9-meter scale without destroying their structural integrity. Carbon fiber, on the other hand, presents a critical thermal paradox during atmospheric re-entry. Because its coefficient of thermal expansion differs drastically from the ceramic heat shield tiles, the extreme temperature shifts in space would cause a 50-meter carbon hull to expand or contract by up to 2 centimeters. This would simply pop the protective heat tiles right off the ship. And then there was the cost. Carbon fiber was running around $130,000 per ton. Stainless steel? Just $3,000 a ton. Even better, stainless steel actually gets stronger when subjected to the deep freeze temperatures of liquid methane and oxygen. And during re-entry, where fiber carbon loses its strength at around 200 degrees Celsius, steel maintains its robust structural integrity all the way up to 800 degrees Celsius. SpaceX tore down their massive carbon fiber tents in Los Angeles and moved operations to the southern coast of Texas. The future of interplanetary travel would be forged in steel. Starhopper and the belly flop. In early 2019, at a remote facility in Boca Chica, Texas, a bizarre water tower-like vehicle dubbed Starhopper took shape. It was welded together outdoors, literally with the help of commercial water tower construction companies. But beneath its crude exterior, it was validating the highly complex full-flow staged combustion of the new methane Raptor engines. In August 2019, Starhopper executed an astonishing 150-meter lateral hop, proving that flying a heavy steel cylinder on liquid methane was entirely possible. This kicked off the era of active failure testing with the serial number, or SN series. The early prototypes, SN1, SN3, and SN4, were sequentially obliterated on the test stand. SN3 collapsed when ground support equipment failed to manage pressure differentials, causing the lower oxygen tank to implode under the sheer weight of the methane tank above it. SN4 suffered a catastrophic explosion when a quick disconnect umbilical leaked a massive cloud of flammable methane. But every explosion yielded gigabytes of crucial telemetry, leading to immediate welding and metallurgical redesigns. Then came the atmospheric tests, designed to validate the most radical aerodynamic concept of the entire program, the belly flop maneuver. Unlike the Apollo capsules, Starship is designed to bleed off its orbital velocity by falling out of the sky horizontally, using its massive cylindrical belly to slam into the atmosphere like a skydiver. It controls this unstable freefall using 4 large, motor-driven aerodynamic flaps. Prototypes SN8 through SN11 flew up to 10 kilometers high, performed the belly flop flawlessly, but met explosive ends during the final vertical landing flip. The harsh G-forces starved the engines of fuel, or pressurized helium leaks caused the rockets to slam into the concrete. But SpaceX's sheer industrial resilience paid off in May 2021 with SN15. Incorporating hundreds of upgrades, including a redesigned thrust puck and highly mature Raptor engines, SN15 launched into the Texas fog, plummeted horizontally, flawlessly reignited its engines, and touched down softly on the pad. The belly flop was officially conquered. Stage 0 and the critical path. With the upper stage proven, SpaceX faced a new massive hurdle, integrating Starship with the colossal Super Heavy booster. This required the creation of an unprecedented launch infrastructure known as Stage 0 to make rapid reusability a reality, functioning closer to a commercial airline than a traditional space program. SpaceX made another counterintuitive decision. They removed the massive landing legs from the booster and the ship. Putting hydraulic legs on a rocket that weighs thousands of tons would eat up an unacceptable amount of payload capacity. Instead, they built a towering integration structure equipped with colossal mechanical arms, affectionately nicknamed Mechazilla, or the chopsticks. The daring plan was to have the massive returning booster hover next to the tower and be caught directly out of midair. This infrastructure was built around a guiding philosophy known internally as the critical path. The critical path dictates that you must constantly eliminate the biggest bottlenecks in production. As launch director Justin Steyer noted, the critical path to Mars is not about avoiding exploded rockets. It's about learning from hardware failures in a controlled way without making the same mechanical mistake twice. Block 1. The integrated flight tests. In April 2023, the Block 1 generation took flight with Integrated Flight Test 1. It served as a stark warning about launch infrastructure. The explosive acoustics of 33 Raptor engines instantly vaporized the concrete pad, creating a rock tornado that shattered the rocket's engines, eventually forcing a self-destruct command in midair. Flight 2 introduced a massive water deluge system that protected the pad, alongside a controversial new technique called hot staging. To avoid the loss of momentum during stage separation, the upper Starship ignited its engines while still attached to the booster, violently blasting the heavy first stage away. It worked, though fluid dynamic issues subsequently destroyed both stages shortly after. Flights 3 and 4 finally consolidated the orbital dynamics. Flight 4 was a masterpiece of endurance, despite the intense plasma of atmospheric re-entry actively melting through a camera arm and burning one of the forward control flaps down to bare metal. The flight software maintained perfect attitude control, resulting in the first successful soft splashdown of both stages in the ocean. But the absolute peak of Block 1 occurred during Flight 5 in October 2024. Falling from the edge of the stratosphere, the Super Heavy booster flipped with unbelievable precision, hovered through its own exhaust smoke, and was perfectly caught in midair by the towering Mechazilla arms. It was a sci-fi dream made real, forever silencing the critics of legless rocket recovery. Flight 6 wrapped up the Block 1 era in late 2024 by deliberately removing heat tiles to test thermal limits, while safety computers intentionally diverted the booster to a safe ocean splashdown when they detected subtle electronic latencies on the tower. Block 2. Pushing the limits. In early 2025, SpaceX rolled out the Block 2 architecture. The changes looked slight to a casual observer, but they were massive internally. The vehicle was stretched to 123.1 meters tall. The internal domes were changed from sharp cones to deep ellipses, significantly increasing the propellant capacity to transport over 1,500 tons of fuel in the upper stage. However, expanding the cryogenic plumbing brought a wave of invisible combustion risks. Flights 7 and 8 ended in rapid disassembly. A ruptured fluid pipe destroyed the entire avionics suite on Flight 7, and a single Raptor engine anomaly on Flight 8 caused a chain reaction that sent the ship spinning out of control. Flight 9 made history by flying the first ever reused Super Heavy, Booster 14-2. But to test the absolute limits of the system, SpaceX intentionally cut off central fuel lines during descent. The aggressive stress test tore the internal manifolds apart, incinerating the booster just before it hit the water. But true to form, SpaceX adapted surgically. They redesigned the rear distribution filters and overhauled the avionics routing. Flights 10 and 11 performed flawlessly, achieving every single orbital and aerodynamic metric without failure. The Block 2 era was officially conquered, paving the way for the ultimate evolution. Block 3 and the present day. As 2026 rolled around, SpaceX unleashed the Block 3, or V3 architecture. This is the machine designed to carry out the heavy lifting for NASA's lunar infrastructure. Standing at a record-breaking 124.4 meters, the V3 ship expanded its vacuum propulsion from 6 engines to a highly dense cluster of 9. This was made possible by the brand-new Raptor 3 engine. The Raptor 3 completely eliminated the need for external heat shields. Instead, it uses advanced regenerative cooling, circulating cryogenic fluids through integrated channels to protect the engine's vital sensors. Despite weighing just 1,525 kilograms, each Raptor 3 pushes chamber pressures to a staggering 350 bar, generating 280 tons of thrust per engine. Down on the booster, the old 4-panel grid fins were replaced by a 3-fin design, reinforced to handle the massive kinetic impacts of catching the heavier vehicle. Flight 12 debuted this hardware in May 2026. The rocket successfully reached orbit, but the aggressive hot staging maneuver caused massive fluid sloshing inside the booster. The fuel was pushed away from the central lines, starving the engines in the vacuum of space. Unable to reignite, the booster plummeted into the Gulf of Mexico at nearly 1,000 miles per hour. Yet, miraculously, the upper stage ship survived the grueling re-entry and nailed a precise ocean landing off the coast of Australia, despite severe damage and missing engines. This brings us to the pivotal events of Flight 13, scheduled for July 16, 2026, the exact anniversary of the Apollo 11 launch. Flight 13 was not just a test, it was an active payload mission, carrying 20 massive Starlink V3 satellites designed to deploy via the ship's payload bay doors. But as the countdown reached zero, automated safety sensors detected a highly specific irregularity in the ignition timing of a few engines in the cluster. Instead of risking the vehicle, the computers triggered a dramatic, instantaneous abort right on the pad. The massive V3 structure remained safe in its iron cradle. This pad abort wasn't a failure. It was a profound demonstration of system maturity. It proved that SpaceX's automated safety protocols were fully capable of saving a multi-billion-dollar infrastructure from a catastrophic launch event, the road to Mars. The engineering behind the Starship program is proving the viability of sustained, human interplanetary life. Moving forward, the V3 architecture will branch out into specialized tanker and depot variants designed to transfer thousands of tons of cryogenic fuel in zero gravity to support lunar missions. Beyond that lies the theoretical Block 4, envisioned to stretch a staggering 142 meters tall, capable of placing over 200 tons of reusable payload into low Earth orbit. In less than a decade, SpaceX transitioned from tethered hops of a rusty water tower in the Texas desert to flying autonomous steel leviathans that can be caught out of the sky by giant robotic arms. They have rewritten the static, archaic paradigms of aerospace engineering. As Starship continues to evolve through deliberate, explosive iterations, it brings the inescapable reality of human colonization on the Moon and the sands of Mars closer than ever before. If you enjoyed this and want to see more technical deep dives into aerospace and automotive systems, make sure to hit the subscribe button. I have a lot more engineering content coming up, and I'd love for you to join the journey. Thanks for watching.